Hello again and welcome back to our macromolecule unit here. We are now going to start entering the world of how we make and break macromolecules. So remember we finished talking about the role of carbon, we had our functional groups, and now you're going to see how these functional groups interact with each other to create really beautiful large structures and actually also help to break down these structures. So we're going to be getting into the 4 different types of macromolecules soon, but first let's talk about how we build macromolecules. So Roman numeral 3 in your notes is going to be macromolecule reactions. And before we get into reactions, really quickly, let's just define what a macromolecule is. So, big letter A. A macromolecule, what these are functional polymers made of repeating units called monomers. So what a polymer is, so if you think of the prefix poly, that's many, and then mer is referring to the word monomer. So the repeating units of monomers, and when you, it's almost, I want you to think of beads on a necklace, or like a nice beaded necklace. Every bead would be a monomer. Once you create and you put all these beads on a string and put the clasp on them and actually make it into a functional necklace, once it gains its function, you have a macromolecule. So a macromolecule has to have a certain function to it, and they are usually polymers made of all these repeating units called monomers. So here we go. Macromolecules are functional molecules made of repeating units called monomers. Oh, and also I'm going to highlight that functional molecules, and we're also going to call them polymers. Polymers made of repeating units called monomers. So if you want to go back to that one example I just gave you, just to bring it down to a practical level, if you're thinking of a necklace, that would be the macromolecule. The beads that make up the necklace, that would be the monomer. Now, just putting a bunch of beads on a string and not giving it a function, that's just any typical polymer. But once you give it the right structure and function, now you have a macromolecule. That makes sense? I could just put a bunch of beads on a string and try to put them around your neck, and it won't work. I have to actually do some different modifications to it, make sure it's functional, make sure it's pretty, make sure it's what you want, and then you have a functional necklace. Therefore, you got a macromolecule. Okay? So, and now let's get into how do we create these macromolecules. Since they are polymers and they're made of repeating units of monomers, the reactions that are used to create these actually link these monomers together one by one. You can almost go back to the necklace example. You're putting another bead on the string. So every time you put another bead on the string, you're doing another reaction to create a longer and longer and longer chain of these monomers that ultimately will become functional and become a macromolecule. So let's talk about that first reaction of creating the macromolecule. This will be big letter B underneath this. So big letter B, I'm going to call the reactions, or actually I'm not going to call it the reactions. We are just going to call it we'll call it macromolecule reactions here. If I could spell. So the macromolecule reactions we're going to focus on, the first one is called a dehydration reaction. So a dehydration reaction, if you think of the word dehydrate, if you're dehydrated, you've been working out, you've been playing in the hot sun, you've been doing whatever, when you're dehydrated, you are lacking water. So the same thing is happening during these reactions. Once we put two things together, what's actually going to happen is that we are going to take water out and produce water. So we're taking water out of the initial equation to produce it later on. So when you're thinking of a dehydration reaction, here is what the definition for this. It's essentially a reaction between two, in our case for macromolecules, a reaction between two monomers that will remove water and links these two monomers together. So it's a reaction that links two monomers together by taking out water. Links two monomers together by removing one molecule of water. Good old H2O. All right, so I'm going to show you a very simple way to build a carbon chain here. So it doesn't have to be a carbon chain. I'm just trying to make a polymer for you, and then we're going to bring this to the real world when we talk about our macromolecules. But here's how the reaction looks. Let's say I have a monomer that looks like this. Actually, I'm going to switch it around for you. And that's my monomer. I want to add that to another one to create two together. So I'm going to add it to itself. We're basically going to do a chemical reaction. And we're going to create some. Okay. So in order for me to make this reaction work, I need to put these two monomers together. So I have a monomer here, and I have a monomer here. And I need to put these two together. And I know when I do a dehydration reaction, every time I put two of these together, I'm going to release a molecule of water. So if you're looking at these two monomers right here, and we know that water is H2O, can you see where I'm going to be getting my water from? Where I'm going to actually I'm literally squeezing water out of this. So if you look at this, I have a C with an OH, and the rest of these are H's. I have a C with an OH, and the rest of these are H's as well. And I want to get an H2O out of this deal. So what's going to happen is this OH group, what's that OH group called again? A hydroxyl group. So this hydroxyl group, it's my functional group. These are the guys that are involved with the reactions. That's the whole reason why we learned that last section. So my OH group is actually going to react with this hydrogen, and these two guys are going to come together to create water. Now here's what it's going to look like as a product. I'm going to shorten this arrow just a bit. Okay, so now I'm going to have a 2-carbon chain with my hydrogens, hydrogen, and my OH. And I'm also going to have water. That's my final product. So when my hydroxyl group grabs this hydrogen, what's happening in reality is that this water is going away, and the energy that is being used that is getting released from getting these two together is actually being also used to create this covalent bond between this carbon and this carbon. So this carbon with these 3 hydrogens are going to go to this carbon with the 2 hydrogens and the OH and connect together. So if you want to piece it together, this guy is this guy, okay, and this guy is this guy. And now my water is all that, okay? Let's do another example, just one more, and then we'll move on to the opposite reaction. Okay, what if time, my starting material doesn't look the same. They're not identical things coming together. What happened here is I have a 3-carbon chain that's already underwent a couple dehydration reactions already. So what I want to do is keep adding to it and adding to it and adding to it. So this 3-carbon guy wants to grab this one. All right, so now you know what to look for. You're trying to find water in all of this. So, and you're keeping it linear. So usually these problems are presented to you in a way that it shouldn't be hard to find how do they fit together. So again, you're going to find the water. You have this 3-carbon chain. Here's your functional group. You have your hydroxyl group. So your hydroxyl group is going to attach itself to a hydrogen, and this portion of this monomer right here is going to attach itself to the side right here while you expel water out. Okay? Let's draw what that looks like on the other side. So if I have a 3-carbon chain plus a 1-carbon, ultimately my product is going to have how many carbons? It's really not hard. You just get used to adding it all up. So now I'm going to have a 4-carbon chain, but how is my 4-carbon chain going to look? You essentially want to redraw everything you see on every carbon. So this carbon has 3 hydrogens attached to it. This carbon has 2, this carbon has 2, and this, the last carbon, is going to have this whole stuff attached to it. So, but always, don't forget, you got to complete your octet, so everybody should be filled. And we can't forget plus water. Okay? So for every dehydration reaction we do, we create 1 molecule of water. All right. So trick question. Not trick question, just you got to think about it. If I have a polymer made of 10 monomers, okay? So I have a 10 monomer polymer. How many molecules of water were created in making that 10 monomer polymer? So if I have, and I'm just going to use a simple symbol. So if I have 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's pretend that every circle represents some monomer. And these can be very large chemical structures to something simple like this. So it doesn't matter. But what you got to know is that this monomer connected to this guy made a bond with this guy. In the process of making a bond, released 1 molecule of water. So in this 10 monomer polymer, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds between the two. So how many molecules of water were made? 9. If you're thinking 10, don't go 10, think 9, because you always got to go 1 less, because the first reaction you have to do involves just putting 2 together. So there's 1 molecule of water, there's my second, there's my third, and there you go. So this would make 9 H2Os at the very end. At the end of the day, you would have 9 waters done. So that is a dehydration reaction. Now let's do the opposite. Because in your bodies, we eat macromolecules all day long. And once we talk about the macromolecules, you're going to be like, this makes sense. But you also have to make these macromolecules inside your cells. So this is the process of what we do in our cells all day long, right now, inside your body. So that's what's going on right now. But when we digest food, you literally are what you eat. So you're going to be breaking down the macromolecules that you eat to create the macromolecules within you. So this is how we make them. Let's talk about how we break them. And it's the exact opposite reaction. In biology, oftentimes you're going to have your yin and yang. You're going to have your exact opposite of whatever you do forward. You're going to do the exact opposite reverse to get back to where you need to be. So if I were just to switch that arrow, that's the next step. So this will be number 2 under big letter B. These reactions are called hydrolysis reactions. So number 2. Hydrolysis reactions. All right, so hydrolysis. We're going to break this word apart. No pun intended, because you're going to see why. The word lysis literally means to break apart. So whenever you hear the word lysis, something is breaking apart, it's blowing up, something's going on in the cell to just take something apart. The word hydro means water. So what we're doing here is we're using water to break apart molecules. That's what's going on. So hydrolysis reactions, we just kind of defined it, uses one molecule of water to remove a monomer from a polymer. Okay? So uses one H2O to remove a monomer from a polymer. Okay, let's go back to our simple example again that we had with carbon. So let's say I have a carbon polymer of just 3 monomers put together. And this is what my polymer looks like. All right. Now I want to take this 3 monomered polymer, we've called it a 3-mer, if you will, or a trimer, if you want to be legit. If you want to call it a trimer. We want to actually turn this into just, we want to make it a 2 + 1 instead of a 3. So what you would do is you would add water to it. I'm actually going to color code this for you so it makes a little more sense. So you're going to add some water to it, and that water is going to go to, we have 2 bonds to work with here. I could either cut it here or I could cut it here. It doesn't really matter. There are reactions inside your cells that are specific for cutting at a certain spot along a polymer. In this example, it doesn't really matter. So let's go ahead and cut right here. Let's cut this tail end guy right off here. So this molecule of water is going to go in and lyse, break up the bond between this part of the polymer and this part of the polymer. Okay? So now that's going to leave me with a 2 carbon chain and a 1 carbon chain. Okay? But now we need to figure out, what does this chain look like now? So what you have to know is that you want to redraw everything the same way you see it, and then we're going to fill in the space in between. All right? So for these 2 carbons, there's nothing but hydrogens on there. So let's fill that in. So I have hydrogen, hydrogen. But I'm missing something here. Let's wait for that for a second. This carbon is looking like this on this side. Copy it over there. Okay. And we don't know what that side of the carbon looks like. So the trick for working with polymers and monomers is to kind of make things look symmetrical on both sides. So the way these monomers work, you know, oops, forgive me, OH. So you know that these monomers, on the right side of the monomer you have an OH, on the left side of the monomer you have a hydrogen. That's just how they linked up together. And so you want to maintain that consistency. And we need to keep a balanced reaction. So in order for us to do this, we know that this water is going to come in and break this bond apart. So if we want to maintain consistency, we're going to put the OH on the right side, just like there's an OH on the right side over here. And on the left side of this guy, we're going to put the H, just like there's an H on the left side over here. Okay, and there's our water. Let's do one more quick example, and then we'll take a break. I'll keep that up here I'll just write up here for a moment. Let's say my monomers, I just have squares to represent any compound I want. And I want to remove one of those squares. So I have 1, 2, 3, 4, 5 squares. Now let's say this is a specific reaction that the water actually needs to break this up into a 3 and a 2. So, and you would be told, here's what's happening as well. But let's take this and We're going to break that bond right there. Okay? So on the other side of this reaction, we're going to see 3 squares plus 2 squares, but we got to put the functional group and the hydrogen in the right spot. Okay? So let's go ahead and just draw the 3 squares and the 2 squares. Actually, I'm going to scoot that over a bit so we don't run out of room. Okay. Now remember, these 3 sets of squares have the hydrogen on the left side. So we're going to keep that there. These 2 have the OH, the hydroxyl group, on the right side. So now this water is being used to provide another two hydrogens and an oxygen. So we're going to have another OH group, another H group. You just want to maintain the consistency that you see. So OHs are on the right side of the boxes, hydrogens are on the left side of the boxes. Now these boxes, remember, are representing big compounds, but I don't want you to worry about that. I want you to remember how these reactions work, because once you get used to them, you can actually work with almost any compound. It's going to be really neat to see. So since OHs are on the right side of all the boxes, we're going to put an OH here, and our hydrogens are on the left side, and that's where our water comes from, right there. Okay? So let's recap really quickly before we move on to the next video. We just learned about what macromolecules are, how they are functional polymers made of repeating units of monomers, and the 2 major reactions that are used to make macromolecules, which are your dehydration reactions, which literally take a molecule of water out to put 2 monomers together. And we also learned about our hydrolysis reactions that use water to literally break the bonds between monomers to deconstruct our functional macromolecules. So thank you again, and I look forward to seeing you next time. We're going to be talking about the 4 major types of macromolecules, which are, we're going to begin with carbohydrates, and then we're going to get to lipids and proteins, and then nucleic acids. So come back with me, and we're going to have a beautiful discussion on carbohydrates coming up next. Thank you.